Hello, and welcome to The Sleepy Scientist. You've found a cozy little corner of the universe where we explore big questions at a wonderfully gentle pace, perfect for winding down, relaxing your mind, and maybe even drifting off before we finish the sentence. Tonight's journey is especially vast. We're going on a cosmic tour of everything, from the tiniest particles to the largest structures in the known universe. We'll float calmly through it all. No stress, no rush. Now, I should warn you, I hope this video isn't too interesting. The goal here is relaxation, not insomnia. But if you do find yourself wide awake pondering the mysteries of space-time at 3 in the morning, well, at least you'll have some excellent space trivia to whisper into the void. Before we begin, I'd love to know, where in the world are you watching from? And what time is it there? Let me know in the comments. It's always a joy to see how far this sleepy little channel travels, and if you enjoy this gentle voyage through the cosmos, whether you're still awake by the end or fast asleep by chapter 2, please consider leaving a like or subscribing. It helps keep this peaceful space going, and I'd be truly grateful. Now, as we begin our journey, a gentle reminder, nothing in this video is intended to be medical advice. If you're having persistent trouble sleeping or any health concerns, it's always best to speak with a professional. Alright, let your body soften, let your mind loosen its grip. We're about to float into the stars together, and there's no need to hold on. Let's start small, really small. No, smaller than that. Picture an atom, already impossibly tiny, then imagine diving deep into its centre, past the cloud of electrons into the dense nucleus. Keep going, even deeper, until you're staring down the very building blocks of reality. That's where we begin, in the quantum realm, the subatomic underworld of the universe. It's not just small, it's mind-bending. Down here, the usual rules of physics don't apply. In fact, the quantum world seems to have a set of rules all its own, written in some mysterious language that even the brightest physicists are still trying to decode. It's a place where particles are also waves, where certainty is a luxury, and where cause and effect take long coffee breaks. It's weird, it's wild, and it's wonderfully fascinating. So what exactly are we talking about? At the tiniest level, everything in the universe is made of fundamental particles. These aren't like tiny marbles or specks of dust. They're more like ripples in invisible fields that fill all of space. Picture the surface of a still pond. Drop a pebble in, and ripples spread outward. Now imagine that pond is an invisible field that exists everywhere in the universe, and the ripple is a particle. That's the modern way physicists think about the universe. Particles are excitations, tiny blips, in these quantum fields. Take the electron, for example. It's one of the most well-known fundamental particles, and it's a ripple in something called the electron field. This field is everywhere, all the time, but when it gets excited in just the right way, an electron appears. It's like the universe saying, aha, here's one now. Then there's the photon, the particle of light. It's a ripple in the electromagnetic field. And let's not forget quarks, which are the little guys that make up protons and neutrons, the stuff inside atomic nuclei. Quarks come in 6 flavors, charmingly named up, down, top, bottom, charm, and strange. These aren't flavors in the ice cream sense, though I'd personally try top quark sorbet if it existed. Now quarks never show up alone. They're always clumped together in groups of 2 or 3, held tightly by particles called gluons. Yes, gluons, as in the glue of the universe. It's a fitting name because these little mediators are responsible for the strong nuclear force, one of the 4 fundamental forces of nature. This strong force is what keeps protons and neutrons bound together inside the nucleus, defying the electromagnetic repulsion between all those positively charged protons. If it weren't for gluons, atoms would fly apart faster than a badly glued school project. While we're on the topic of forces, let's do a quick inventory. There are 4 known fundamental forces in the universe. First, the strong nuclear force, which we just met. Second, the electromagnetic force responsible for electricity, magnetism, and light. Third, the weak nuclear force, which plays a key role in radioactive decay and nuclear fusion. And finally, gravity, the force that holds your feet to the ground, keeps the moon orbiting Earth, and makes black holes black. Oddly enough, gravity is the one we understand the least at the quantum level. It's the weakest of the four forces by a long shot. But when you're dealing with massive objects like planets or stars, its effects become dramatic. In contrast, quantum forces dominate at small scales. For instance, the strong force is about 10,000 times stronger than the electromagnetic force, and the electromagnetic force is far stronger than gravity when it comes to the behavior of atoms. Now let's talk uncertainty. At the quantum level, nothing is ever completely still or certain. This isn't because our measuring tools aren't precise enough, it's because uncertainty is built into the very nature of reality. According to Heisenberg's uncertainty principle, you can't know both the exact position and exact momentum of a particle at the same time. The more precisely you know one, the fuzzier the other becomes. Imagine trying to photograph a hummingbird in flight. You can get a crisp image of its position, or you can focus on its speed, but not both at once. Now apply that principle not to birds but to electrons, and you begin to get a sense of the wiggly, unpredictable nature of the quantum world. Particles blur and shimmer, darting in and out of knowability. It's like the universe is playing hide and seek with itself. Then there's quantum superposition, the idea that a particle can be in multiple states at once, until it's measured. This isn't just theory, it's been demonstrated in experiments again and again. The most famous thought experiment involving superposition is Schrödinger's cat. You've probably heard of it. A cat is placed in a sealed box with a device that has a 50-50 chance of releasing poison, based on a quantum event. Until someone opens the box to check, the cat is both alive and dead. It's not that the cat is in one state and we just don't know. It's that, according to quantum rules, the cat exists in both states simultaneously until observed. Of course, no one's actually done this experiment with a real cat. It's meant to illustrate how strange quantum mechanics can be when scaled up to everyday life. Fortunately, cats don't follow quantum mechanics. They follow their own laws of physics, which usually involve knocking things off tables at 3 a.m. Let's not forget quantum entanglement, perhaps the most mysterious phenomenon of all. When two particles become entangled, their states are linked, no matter how far apart they are. Change one, and the other responds instantly, even if it's on the other side of the universe. Einstein famously called this spooky action at a distance, and while he wasn't a fan of the idea, it's been proven to happen. Entanglement is real, and it's been observed in the lab many times over. But how does it work? That's still a bit of a puzzle. Information can't travel faster than light, so how can one particle know what's happening to its partner instantly? The best explanation so far is that entangled particles share a kind of quantum state that is resolved only when one is observed. It's not that the second particle changes to match the first, it's that both were part of the same invisible equation all along. If your brain feels like it's doing somersaults at this point, that's completely normal. Even physicists describe quantum mechanics as something you never really understand. You just get used to how weird it is. Now, what about the space all this happens in? Is empty space really empty? Not at all. In quantum field theory, even a perfect vacuum teems with activity. Virtual particles constantly pop into and out of existence, borrowing energy from the vacuum in fleeting blips that vanish before they can be directly observed. This is called quantum vacuum fluctuation, and it's not just theoretical. It has measurable effects, like the Casimir effect, where two uncharged metal plates placed very close together in a vacuum are mysteriously pulled toward each other. It's as if the universe can't sit still, not even in its quietest corners. The vacuum is more like a restless ocean than a still void, bubbling with invisible possibilities. Quantum mechanics may sound like science fiction, but it's real science, and it powers much of the technology we use today. Lasers, semiconductors, and even GPS systems all rely on quantum principles. Without quantum physics, there would be no smartphones, no computers, and no sleepy YouTube videos about the mysteries of the universe. But even with all our progress, the quantum world remains deeply mysterious. For instance, the so-called measurement problem still haunts physicists. What exactly causes a quantum system to collapse into a definite state when observed? Is consciousness involved? Is the universe keeping secrets from us? No one knows for sure. Still, we continue to explore, because understanding the quantum realm isn't just about figuring out the tiniest parts of the universe. It's about uncovering the rules that shape everything, from the blinking cursor on your screen to the stars overhead. It all starts here, in a place where particles shimmer like possibilities, where fields ripple through the vacuum, and where reality itself seems to be composed of probabilities more than certainties. It's a strange, beautiful world, and it's humming quietly beneath everything you see. Atoms. They're the quiet architects of the universe. Everything you can see, touch, smell, and accidentally trip over in the dark is made from them. From the skin on your fingertips to the stars hanging softly in the night sky, all of it, every last speck, is built from atoms. But don't be fooled by their ubiquity. Atoms are not simple. They are marvels of cosmic engineering. They are tiny, yes, so tiny that a single grain of sand contains more atoms than there are stars in the observable universe. But each one is an intricate structure that holds the memory of stars and the promise of chemistry. Let's start with the basics. The word atom comes from the Greek word atomos, meaning indivisible. The ancient philosophers who named it thought atoms were the smallest possible pieces of matter, solid, uncuttable particles that made up everything. But nature, as always, is a bit more complicated. We now know that atoms are not indivisible at all. They're composed of even smaller particles, protons, neutrons, and electrons. Picture an atom like a solar system. This is not entirely accurate, but it gives us a useful visual. At the centre is the nucleus, a dense, compact core made of protons and neutrons. Around this nucleus, electrons flit and flutter like hyperactive bees in a vast and mostly empty space. But don't let the word orbit fool you. Electrons don't actually circle the nucleus in neat paths like planets. Instead, they exist in fuzzy, probabilistic clouds called orbitals, where we can only estimate the likelihood of finding an electron in a given region. Let's take a simple atom. Hydrogen. Hydrogen is the lightest and most abundant element in the universe. It has one proton, one electron, and usually no neutron. That's it. It's the cosmic equivalent of a studio apartment. But despite its simplicity, hydrogen is incredibly important. It's the building block of stars. It's what fuels the fusion reactions that power the sun and give life to our little blue planet. In fact, if atoms were characters in a play, hydrogen would be the quietly competent understudy who ends up saving the day. Next in line is helium, the second element on the periodic table. With 2 protons, 2 neutrons, and 2 electrons, helium is like hydrogen's older, more stable sibling. It's inert, gentle, and refuses to react with almost anything, a true wallflower at the chemical party. But it's also what makes balloons float, and what you inhale if you want to sound like a chipmunk, which, while not scientifically necessary, is undeniably entertaining. As we move through the periodic table, atoms get larger and more complex. The number of protons in an atom's nucleus is called its atomic number, and it determines what element that atom is. Carbon, for example, has 6 protons, oxygen has 8, gold has 79, uranium has 92. Each step up the periodic ladder introduces new combinations of protons, neutrons, and electrons, each resulting in unique behaviours and chemical properties. But here's the part that's truly mind-bending. Atoms are almost entirely empty space. If the nucleus of an atom were the size of a golf ball, the nearest electrons would be orbiting nearly a kilometre away. and the nucleus itself is unbelievably dense. If you could compress the nuclei from every atom in your body into a single point, you'd have something as small as a speck of dust, but weighing as much as an aircraft carrier. This is the kind of physics that sounds like it came from a sci-fi novel, but is in fact your everyday reality. Now let's take a closer look at the three main subatomic particles. First, protons. These positively charged particles live in the nucleus and determine an atom's identity. Add a proton, and you change the element entirely. 1 proton, hydrogen. 2 protons, helium. 3, lithium. And so on. Protons are made of even smaller particles called quarks, specifically 2 up quarks and 1 down quark, held together by those ever-dedicated gluons we mentioned earlier. Next, neutrons. They live right alongside protons in the nucleus and carry no charge, hence the name neutron. Their job is to help hold the nucleus together. Without neutrons, the repulsive forces between positively charged protons would blow the nucleus apart. Neutrons act like nuclear peacekeepers, providing just enough glue to keep things stable. Like protons, neutrons are also made of quarks, 1 up quark and 2 down quarks. And finally, electrons. These tiny, negatively charged particles are astonishingly light, over 1,800 times lighter than a proton. They buzz around the nucleus in their probabilistic clouds, and their arrangement determines how atoms bond with each other to form molecules. Electrons are the social butterflies of the atomic world. They're the ones making connections, forming chemical bonds, and giving structure to everything from water to DNA to the deliciously complicated compound that is chocolate. Now let's talk energy levels. Electrons don't just float around randomly. They exist in discrete energy levels or shells. Think of them like floors in an apartment building. Electrons prefer to live on the lowest available floor, that is, the one that requires the least energy. But if you give them a little extra energy, say, from light or heat, they can jump up to a higher floor, and when they fall back down, they release that energy in the form of light. This is how neon signs glow, how fireworks shine, and how the stars twinkle in the night sky. The number and arrangement of electrons in an atom's outer shell are what determine its chemical behavior. Atoms are always trying to achieve a full outer shell, like someone trying to fill the last seat at a dinner table. Sometimes they give away electrons, sometimes they take them, and sometimes they share. These interactions are what we call chemical bonds, and they're responsible for building everything from raindrops to roses. There are different kinds of bonds. Ionic bonds happen when one atom donates an electron to another, like sodium giving one to chlorine to make salt. Covalent bonds involve sharing electrons, as in the classic example of 2 hydrogen atoms and 1 oxygen atom holding hands to form water. There are also metallic bonds, hydrogen bonds, and a host of more exotic interactions, but they all stem from the same fundamental desire: atoms trying to achieve stability. Isotopes are another fascinating atomic twist. An isotope is a version of an element with the same number of protons but a different number of neutrons. Carbon, for example, typically has 6 protons and 6 neutrons. But carbon-14 has 8 neutrons instead. It's still carbon, it still behaves chemically like carbon, but it's heavier and in this case radioactive. Scientists use isotopes like carbon-14 for radiocarbon dating, helping us peer into the past and figure out how old fossils, bones and ancient campfires might be. Radioactive atoms are those with unstable nuclei. Over time, these atoms release energy in the form of radiation, as they decay into more stable forms. This process can take milliseconds or millions of years, depending on the element. It's a natural part of the atomic life cycle, and one that has both peaceful and powerful applications, from medical imaging to nuclear energy to, unfortunately, nuclear weapons. But most atoms are stable. They just exist quietly, buzzing with potential energy, drifting through the world until they find a purpose, perhaps becoming part of a leaf, a bloodstream or a meteor streaking across the sky. And here's a thought that might help you sleep tonight. Nearly every atom in your body was forged in the heart of a star. The hydrogen atoms were formed in the first few minutes after the Big Bang. But the heavier elements, carbon, nitrogen, oxygen, iron, were cooked in stellar furnaces and scattered across space by exploding stars. Every breath you take contains the ashes of ancient suns. You are quite literally made of star stuff, as Carl Sagan so beautifully put it. Atoms don't just make up the things around us. They connect us across time and space. The calcium in your bones might have once been part of a dinosaur. The oxygen you inhale might have passed through the leaves of a prehistoric tree. The atoms in your cup of tea might have once danced inside the belly of a comet. Matter is not created or destroyed, only transformed. The atoms in your body were here long before you, and they'll still be here long after. So the next time you hold something in your hand, whether it's a pencil, a pebble, or a pillow, just remember, you're not just holding an object. You're holding a constellation of atoms, ancient and eternal, woven into a shape by the laws of physics and the dance of electrons. It's humbling, it's magical, and it's happening all the time in everything you see. Atoms, it turns out, are not just tiny things floating in space. They're storytellers. They carry the history of the universe, piece by piece, atom by atom. And if you listen closely, they're still telling it now. Atoms by themselves are impressive, no doubt. Tiny, ancient, full of star-forged elegance. But what really makes them sing, the part where the universe starts cooking up everything from clouds to cacti to cheese, is chemistry. Chemistry is what happens when atoms get social. It's the grand mixer party of the periodic table, and everyone's bringing something to share. Imagine atoms at a cosmic potluck. Hydrogen shows up early as usual, looking a little plain but undeniably essential. Oxygen follows with a dramatic flair and immediately bonds with hydrogen to form water, the universe's most celebrated refreshment. Carbon, of course, arrives with a full entourage and starts building complex molecular pyramids before the appetizers are even served. This is what chemistry is. The art and science of atoms combining, swapping electrons, creating entirely new substances with properties that none of the individual elements had on their own. It's like musical notes forming chords, or individual letters turning into poetry. The parts are simple, but the combinations, infinitely rich. Let's start with the most fundamental players. The periodic table is essentially the seating chart for this atomic potluck. Each element has its own personality, shaped mostly by the number of electrons in its outer shell, what chemists call the valence shell. These outer electrons are the ones involved in bonding, and atoms are always trying to either fill or empty their valence shells to achieve stability. That's why sodium, which has one lonely electron in its outer shell, is so eager to hand it off. It's the friend who brings a side dish just to get rid of it. Chlorine, on the other hand, is one electron short of a full outer shell, so it's all too happy to accept sodium's gift. When these two bond, they form sodium chloride, otherwise known as table salt. Separately, sodium is a soft, reactive metal that explodes in water, and chlorine is a poisonous green gas. But together they season your French fries. Chemistry is full of surprises like that. Chemical bonds come in a few main varieties. Ionic bonds, like the one between sodium and chlorine, occur when atoms transfer electrons. One gives, one takes, and the result is a stable compound with charged ions that are held together by electrostatic attraction. It's a bit like a cosmic game of hot potato, only no one gets burned. Then there are covalent bonds where atoms share electrons more equitably. This is what happens when two hydrogen atoms and one oxygen atom decide to hold hands, each contributing electrons to create water. Covalent bonds are the true team players of the molecular world. They show up in sugars, proteins, DNA, basically all the stuff of life. Sometimes the sharing isn't quite equal. In a polar covalent bond, the electrons are pulled a little closer to one atom than the other, creating slight positive and negative poles in the molecule. Water is a classic example. Oxygen hogs the electrons a bit, giving water its unique properties, like surface tension, the ability to dissolve all sorts of substances, and the tendency to form beautiful, delicate snowflakes when it freezes. There's also metallic bonding, which is more like a free-for-all. In metals, electrons are not bound to individual atoms, but roam freely in a sort of electron sea. This gives metals their characteristic properties. They conduct electricity, they're malleable, and they have that lovely reflective shine. They're like atoms in a dance hall with electrons gliding around the floor, never committing to just one partner. Now, once atoms bond into molecules, the fun really begins. Molecules can be small, like the diatomic oxygen you breathe, or staggeringly large, like DNA, which carries the instructions for building entire organisms. Chemistry is the architecture of life, and molecules are its bricks and blueprints. Take carbon, for instance. Carbon is a bit of a show-off. It can form 4 stable covalent bonds, which makes it incredibly versatile. It's the backbone of organic chemistry, the chemistry of life. Carbon can create rings, chains, branches, double bonds, triple bonds. It can bond with itself endlessly, building everything from methane to muscle tissue. If atoms were Lego bricks, carbon would be the piece you can use to build anything from a spaceship to a spaghetti monster. Thanks to carbon's versatility, we get hydrocarbons, molecules made of carbon and hydrogen, which are the basis for fuels like gasoline and natural gas. We also get carbohydrates, proteins, lipids, and nucleic acids, all of which play critical roles in biology. Carbohydrates provide energy. Proteins do the heavy lifting, building and repairing tissues. Lipids make up cell membranes and store energy. And nucleic acids, like DNA and RNA, carry genetic information. Even the air around you is full of chemistry. The nitrogen you're breathing makes up about 78% of Earth's atmosphere. It's mostly inert and doesn't react much under normal conditions, which is a good thing. It means you're not constantly surrounded by fiery explosions. Oxygen, at about 21%, is more reactive. It's essential for respiration, where your cells use it to help release energy from food. Then there's carbon dioxide, a trace gas that plays an outsized role. Plants use it during photosynthesis, combining it with sunlight and water to create glucose and release oxygen. You exhale it as a waste product. And, as we've come to learn, it also traps heat in Earth's atmosphere, contributing to climate change. Water chemistry deserves its own moment in the spotlight. Water is a simple molecule, 2 hydrogens and 1 oxygen, but it has astonishing properties. It can dissolve more substances than any other liquid, earning it the title of universal solvent. It expands when it freezes, which is why ice floats, a rare and life-preserving quirk. It also has a high specific heat, meaning it takes a lot of energy to change its temperature. That's one reason oceans help regulate Earth's climate, keeping things relatively stable. Let's not forget acids and bases. These are substances that deal with hydrogen ions. Acids donate hydrogen ions, bases accept them. The pH scale measures how acidic or basic a solution is, ranging from 0 to 14. Pure water is neutral at 7. Lemon juice sits around 2, quite acidic. Soap might be at 9 or 10, slightly basic. Your stomach? It's full of hydrochloric acid, around pH 1 or 2, which helps digest food but is thankfully kept in check by your stomach lining. Without it, tacos would be a lot more dangerous. Chemistry also explains why you can't mix certain things. Oil and water, for example, famously don't get along. That's because water molecules are polar. They have a positive end and a negative end, while oil molecules are non-polar. Water sticks to itself and excludes oil, like an exclusive club with a strict dress code. You can force them together temporarily with an emulsifier, like in mayonnaise, but left alone, they'll drift apart again. Chemistry is picky like that. Even colour is chemistry. The colours of leaves, flowers and pigments all come from molecules absorbing certain wavelengths of light and reflecting others. Chlorophyll makes plants green by absorbing red and blue light and reflecting green. Carotenoids give carrots their orange hue. Anthocyanins turn leaves red and purple in the fall, and melanin gives skin and hair its colour, protecting against ultraviolet radiation in the process. Smells and tastes? Also chemistry. The flavour of garlic comes from sulphur-containing compounds. Minty freshness comes from menthol. Vanillin gives vanilla its warm, sweet aroma. These are all molecules interacting with receptors in your nose and mouth, triggering complex neurological responses. That delicious cup of coffee you had this morning? A bubbling symphony of volatile organic compounds, acids, and alkaloids, all doing chemistry in a mug. In the realm of synthetic chemistry, scientists are crafting new materials all the time. Plastics, pharmaceuticals, superconductors, nanomaterials. These substances aren't found in nature but are made by rearranging atoms in specific ways to achieve desired properties. It's chemistry as alchemy, turning raw elements into tools, medicines, and technologies that shape our daily lives. Yet for all its complexity, chemistry is built on simple rules. Atoms want stability, electrons want balance, charges attract, reactions seek equilibrium. And from these basic desires emerge the bewildering variety of matter and behaviour we see in the universe. So whether it's rust forming on a bicycle, yeast fermenting in bread, or the sparkle of a diamond, chemistry is everywhere. It's what allows soap to clean, batteries to charge, and fireflies to glow. It's the quiet architect behind every breath you take and every meal you enjoy. And it's all happening at the atomic level. Tiny particles dancing, exchanging electrons, making and breaking bonds. In a way, chemistry is the universe's love language. It's how atoms reach out to one another. It's the handshake, the embrace, the spark of connection. It's the reason that a cloud can form, a tree can grow, or a person can fall in love over the scent of fresh rain on warm pavement. Every reaction tells a story, and once you start listening, you realize the world is whispering in molecules, light and gravity, two forces that seem to live in entirely different corners of the cosmic toolbox. One brings us warmth, vision, photosynthesis, and the occasional dramatic sunset. The other quietly holds everything together, from your body to the moon to entire galaxies. One zips through space at an eye-watering speed, while the other patiently curves the fabric of the universe itself. They don't seem like they'd have much in common, but in the grand story of physics they are deeply intertwined, and both are far more fascinating than they first appear. Let's start with light. It's something we often take for granted. It pours through windows, flickers from screens, and dances on puddles. But what is it really? Light is a form of electromagnetic radiation, waves of electric and magnetic fields oscillating through space. But unlike sound waves, which need air or water to travel through, light can move through the vacuum of space just fine. In fact, that's one of its most impressive tricks. Light doesn't need anything to carry it. It's a self-sufficient wave. It creates electric and magnetic fields as it moves, and those fields generate each other in a perfect perpetual leapfrog. This is why it can travel across the emptiness of space from distant stars and galaxies and still reach your eyes, carrying ancient messages from the far reaches of the cosmos. But light isn't just a wave, it's also a particle. This duality is one of the strangest and most wonderful ideas in physics. Light comes in discrete packets of energy called photons. Each photon is a tiny quantum of light, with no mass, always moving at the speed of light, and carrying just enough energy to get its job done, whether that's warming your skin, powering a solar panel, or bouncing off a mirror. This wave-particle duality of light is at the heart of quantum mechanics. In some experiments, light behaves like a wave, spreading out and interfering with itself. In others, it acts like a particle, hitting one spot at a time. It's not that light is switching between identities, it's that our classical definitions don't fully apply. Light is just being light. It plays by quantum rules, which are more flexible and strange than anything we're used to in everyday life. Light travels incredibly fast. In a vacuum, it zips along at about 300,000 kilometers per second. That's fast enough to circle Earth 7.5 times in a single second. And yet, for all its speed, light can still be slowed down. When it passes through materials like glass, water, or even diamond, it interacts with the atoms inside, getting briefly absorbed and re-emitted in a game of quantum hopscotch. This delays its progress, giving the illusion that it's moving more slowly. But the moment it escapes into a vacuum again, off it goes at full speed, never tiring, never aging. Now, here's where things get interesting. According to Einstein's theory of relativity, the speed of light is not just fast, it's the universal speed limit. Nothing with mass can ever reach or exceed it. No spaceship, no signal, no gossip faster than light speed. Photons are unique because they have no mass, which allows them to move at this ultimate speed without ever needing to accelerate. But the implications of the speed of light go deeper than speed itself. They warp our very understanding of time and space. As you approach the speed of light, time slows down for you relative to someone standing still. This isn't science fiction. It's been proven in countless experiments. Astronauts aboard the International Space Station age just a tiny bit more slowly than people on Earth due to their high-speed orbit. It's a minuscule effect, but measurable and real. Now, take that same idea and imagine travelling near the speed of light across the galaxy. For you, the trip might feel like a few months. For people back on Earth, decades could pass. This strange stretching and compressing of time and space is part of what Einstein revealed in his theory of special relativity. It's not just that clocks run differently, it's that space and time are woven together into something called space-time. And this brings us to gravity. For centuries, gravity was thought of as a force that objects exerted on each other. Newton's apple falls to the ground because Earth pulls on it. The moon stays in orbit because of Earth's gravitational tug. This view worked beautifully for predicting planetary motion and building bridges that don't collapse. But Einstein saw something deeper. In his general theory of relativity, gravity is not a force in the traditional sense. It's the warping of space-time caused by mass and energy. Massive objects like Earth or the Sun bend the fabric of space-time, and other objects move along the curves in that fabric. When you drop a ball, it falls not because Earth is pulling on it, but because the ball is following the curved path that space-time tells it to. This is often illustrated with the famous rubber sheet analogy. Imagine a stretched sheet of fabric. Place a heavy bowling ball in the centre. It causes a dent. Now roll a marble across the sheet. The marble curves inward, not because it's being pulled, but because the surface it's rolling on is no longer flat. That's gravity, not a mysterious force acting at a distance, but a bending of the very arena in which everything plays out. Light too is affected by this curvature. When a beam of light passes near a massive object, like a star or a galaxy, its path bends. This phenomenon is called gravitational lensing, and it has been observed many times. Massive galaxies can distort the light from more distant galaxies behind them, creating arcs and rings in the sky, cosmic mirages that allow astronomers to study things that would otherwise remain hidden. Gravitational lensing has become one of the best tools for mapping dark matter, the invisible substance that makes up most of the matter in the universe. Even though dark matter doesn't emit light or interact with it directly, its gravity still warps space-time and bends the paths of light passing nearby. By measuring these distortions, scientists can figure out where dark matter is hiding. Gravity also affects time. In regions of stronger gravity, like near a planet or a black hole, time actually ticks more slowly. This is known as gravitational time dilation. If you spent time near the edge of a black hole just hovering at a safe distance, you'd age more slowly than someone farther away. The deeper you are in a gravitational well, the slower time moves for you. This isn't a metaphor, it's measurable, precise, and absolutely real. One of the most stunning confirmations of general relativity came from the detection of gravitational waves, ripples in space-time caused by massive accelerating bodies, like two black holes spiraling into each other. These waves were predicted by Einstein over 100 years ago, but they weren't detected until 2015, when the LIGO Observatory recorded the faint stretching and squeezing of space-time caused by a collision that occurred over 1 billion light-years away. Gravitational waves are incredibly subtle, thousands of times smaller than the width of a proton, but they carry an enormous amount of information. They tell us not just that an event happened, but how massive the objects were, how fast they were moving, and what kind of dance they performed before merging. We are now listening to the universe in a whole new way, not just looking at light, but feeling the tremors of gravity itself. Despite its elegance, gravity remains the least understood of the fundamental forces. Unlike electromagnetism or the nuclear forces, gravity stubbornly refuses to be unified with quantum mechanics. It's like the quiet sibling who shows up to every family reunion, but won't tell you what they do for a living. The quest to find a quantum theory of gravity, a way to describe gravity at the smaller scales, is one of the biggest open questions in physics. Some theories propose particles called gravitons, which would mediate the force of gravity like photons do for electromagnetism. Others explore more exotic ideas, like string theory or loop quantum gravity. These are deep waters, full of equations, thought experiments, and hopeful speculation. But for now, gravity remains both familiar and mysterious. It's the force that holds your coffee mug to the table and shapes the orbits of planets. And yet it may also hold the key to a deeper understanding of space, time, and everything in between. Meanwhile, light continues to astonish. It allows us to peer into the past, to see galaxies as they were billions of years ago. It carries the signature of every atom it touches, letting astronomers decode the chemical makeup of stars, planets, and nebulae. It paints the auroras in the sky and gives sunsets their fire. It reveals, illuminates, and inspires. Together, light and gravity shape the universe in ways that are both visible and invisible. One brings things together, the other shows us where everything is. One curves the map, the other travels across it. One pulls, the other flies. And both, in their own strange and beautiful ways, help us understand where we are and how we fit into this vast cosmic web. So the next time sunlight filters through your window, or you glance at the moon hanging quietly in the sky, take a moment to appreciate the invisible dance unfolding all around you. Light moving across time, gravity shaping your every step. Forces so fundamental we forget they're even there, until we stop, breathe, and marvel at the invisible threads that hold the universe together. Welcome to our cosmic cul-de-sac, the solar system, our own tiny neighbourhood in the great cosmic sprawl. It's a rather charming setup. Just one modest star at the centre, a handful of planets circling dutifully around it, and a supporting cast of moons, comets, asteroids, and dust. It might not be the flashiest system in the galaxy, but it's home. And as far as we know, it's the only one with coffee, books, and the occasional cat meme. Let's begin with the Sun, the radiant monarch of our solar system. It contains over 99.8% of the entire system's mass. That's right. Almost everything in the solar system is, quite literally, part of the Sun. Everything else, the planets, moons, asteroids, and you sitting comfortably wherever you are, is just debris, cosmic afterthoughts swirling around a gigantic fusion-powered sphere of plasma. The Sun is a yellow dwarf, which sounds delightfully humble, but it's anything but small. With a diameter of about 1.4 million kilometres, you could fit more than 1 million Earths inside it. It shines because of nuclear fusion, the process of squashing hydrogen atoms together so tightly that they merge into helium, releasing an incredible amount of energy in the process. That energy then takes a leisurely 100,000 years to wiggle its way from the Sun's core to the surface, before flying off into space in just over 8 minutes to reach Earth. That sunlight touching your skin today started its journey long before modern humans existed. Moving outward from the Sun, the first stop is Mercury, tiny, cratered, and fast. It orbits the Sun in just 88 days. Mercury doesn't have much of an atmosphere, so daytime temperatures can soar to over 400 degrees Celsius, while nighttime temperatures can drop to nearly minus 180 degrees Celsius. It's a world of extremes, battered and baked, quietly racing around the Sun like a cosmic sprinter. Next comes Venus, Earth's strange twin. Roughly the same size and mass, but that's where the similarities end. Venus is a sweltering nightmare. Its thick atmosphere is made mostly of carbon dioxide, with clouds of sulfuric acid, and it traps heat with astonishing efficiency. The surface temperature hovers around 460 degrees Celsius, hot enough to melt lead. And to make things even more unsettling, Venus rotates backwards and extremely slowly. A day on Venus lasts longer than its year. If you were to stand on its surface, which, to be clear, is not recommended, you'd see the sun rise in the west and set in the east, all while slowly being cooked and crushed. Romantic, isn't it? Then, blessedly, we arrive at Earth. A pale blue dot with oceans, continents, and an atmosphere just right for life. Earth is the only planet we know of that supports life, and it owes much of that to its balanced conditions. Water in all three states, a protective magnetic field, plate tectonics to recycle nutrients, and just the right distance from the sun, not too hot, not too cold. It's the Goldilocks planet, and we are its fortunate guests. Earth also has a moon, a relatively large one for its size, which helps stabilize its tilt and climate. The moon formed about 4.5 billion years ago, likely from the debris of a massive collision between Earth and a Mars-sized object. Today, it gently tugs on our oceans, lighting up the night sky and inspiring poets and scientists alike. Next in line is Mars, the rusty wanderer. With its dusty red surface, towering volcanoes, and ancient riverbeds, Mars is perhaps the most studied planet besides Earth. It's about half Earth's size and has a thin atmosphere, mostly carbon dioxide. Although today it's dry and barren, evidence suggests it once had liquid water, lakes, and maybe even oceans. Robotic explorers have trundled across its surface, searching for clues to its past. And one day, if all goes well, humans may walk there too, leaving boot prints in ancient Martian dust. Beyond Mars lies the asteroid belt, a region filled with rocky remnants from the early solar system. Most of these objects are small and irregularly shaped, but a few are quite large. The biggest, Ceres, is so massive it's considered a dwarf planet. These asteroids are leftovers, chunks that never quite made it into full-fledged planets. They're a bit like the crumbs left behind after baking a cosmic cake. Past the asteroid belt, we enter the domain of the giants. First comes Jupiter, the king of the planets. It's a gas giant more than 11 times the diameter of Earth and over 300 times as massive. If planets had egos, Jupiter's would be massive, but it's earned it. Its atmosphere is a swirling canvas of storms and stripes, with the famous Great Red Spot, a hurricane bigger than Earth itself, raging for centuries. Jupiter doesn't have a solid surface, just increasingly dense layers of hydrogen and helium leading down to a possible core, and it's surrounded by at least 95 moons, each with its own story. One of them, Europa, has a subsurface ocean that may harbour life. Another, Io, is the most volcanically active body in the solar system. Next is Saturn, the showstopper. Saturn is also a gas giant, but it's best known for its spectacular ring system. These rings are made of ice and rock, ranging in size from grains of sand to small buildings, and they stretch out over hundreds of thousands of kilometres. Saturn itself is less dense than water, meaning if you had a bathtub big enough, Saturn would float. It also has a large family of moons, including Titan, which has thick clouds, lakes of liquid methane, and a rich complex chemistry that tantalizes scientists with the possibility of alien life. Then we come to Uranus, the awkward middle child of the outer planets. It's an ice giant, pale blue in colour due to methane in its atmosphere, and it spins on its side. Its axis is tilted by more than 90 degrees, possibly the result of a colossal impact long ago. This sideways rotation leads to extreme seasons that last decades. Uranus also has rings, although they're faint and dark, and it has 27 known moons with names borrowed from Shakespearean characters. Farther still is Neptune, the last of the official planets, deep blue, mysterious, and intensely windy. It's another ice giant, with a dynamic atmosphere and supersonic winds, the fastest in the solar system. One of its moons, Triton, orbits backwards and is thought to be a captured object from the Kuiper Belt. Triton also has geysers of nitrogen ice, hinting at geological activity in this frigid distant world. Beyond Neptune lies the Kuiper Belt, a vast region filled with icy objects, dwarf planets, and comets. This is the realm of Pluto, once the 9th planet, now reclassified as a dwarf planet. Pluto is small, cold, and surprisingly complex. When the New Horizons spacecraft flew past it in 2015, it revealed a world with mountains, glaciers, and a giant heart-shaped plain. Despite its demotion, Pluto remains a favourite, plucky and mysterious, orbiting in the far reaches of our solar system with its 5 moons, including the large companion Charon. Even farther out lies the Oort cloud, a hypothetical shell of icy bodies surrounding the solar system at a distance so vast it takes light more than a year to cross it. It's from here that long-period comets are thought to originate, drifting in from the cold depths of interstellar space, occasionally visiting the inner solar system before returning to the dark. And all of this, the planets, moons, belts, clouds, and comets, orbits in the same general plane around the Sun, held together by gravity and shaped by billions of years of evolution. The solar system is dynamic, ever-changing. Planets wobble, moons shift, asteroids collide. It's not a clockwork model of perfect harmony. It's a living, breathing system. What's remarkable is how much we've learned from our little corner of space. Robotic spacecraft have visited every planet, and some have ventured beyond. Voyager 1 and Voyager 2, launched in the late 1970s, are now in interstellar space, carrying golden records with sounds and images from Earth, a message in a bottle for any intelligent life that might one day find them. For all its wonder, the solar system is still just one star's worth of material. The Milky Way contains hundreds of billions of stars, each potentially hosting its own planets, moons, and mysteries. But even if we never leave our solar system, there's more than enough here to keep us busy for lifetimes. From volcanic moons to methane lakes to the subtle dance of gravitational forces, it's a reminder that even in the cosmic suburbs, things are anything but dull. So next time you look up at the night sky, remember, you live in a beautiful, intricate neighbourhood, spinning around a star, part of a story 4.5 billion years in the making. The solar system isn't just where we are, it's who we are. A collection of worlds, large and small, light and dark, silent and stormy, all spinning together in the gentle grip of sunlight. Stars are a bit like people. They're born, they grow up, they burn with intensity for a time, and eventually they reach the end of their journey. Some go out quietly, others erupt in dazzling cataclysmic finales that can be seen across galaxies. And while stars don't worry about deadlines or taxes, they do live full, complex lives governed by mass, gravity, and the constant tug-of-war between collapse and explosion. At first glance, a star might just seem like a glowing dot in the sky, a pretty point of light that twinkles and winks. But up close, a star is anything but delicate. It's a raging furnace of nuclear fusion, a sphere of superheated plasma where the laws of physics flex their muscles in magnificent ways. And the story of a star's life is really the story of how the universe builds, changes, and recycles itself. Let's begin with how stars are born. Every star starts its life in a cloud, a massive, cold cloud of gas and dust known as a nebula. These cosmic nurseries are scattered throughout galaxies, and they can span dozens or even hundreds of light years. They're dark, dense, and quiet, until something disturbs them. It could be a nearby supernova or a gentle nudge from gravitational tides. Whatever the trigger, a portion of the cloud begins to collapse under its own gravity. As this cloud contracts, the gas and dust gather into a denser core and it starts to heat up. This growing ball is called a protostar. It's not a star yet, it's more like a star in waiting. Gravity continues to pull material inward, compressing it tighter and tighter. As the pressure and temperature increase, the core gets hotter, millions of degrees hotter. Eventually, a critical point is reached. The temperature and pressure become so intense that hydrogen atoms start to fuse. In other words, they merge together to form helium, and in doing so, release energy. This process is called nuclear fusion, and it's the moment a protostar becomes a true star. It's kind of like flipping a cosmic light switch. The star ignites, begins to shine, and joins the galactic stage. The energy released by fusion pushes outward, creating an internal pressure that balances the inward pull of gravity. This delicate balance is what keeps a star stable for most of its life. It's a bit like a balloon. Gravity wants to make the balloon collapse, but the pressure inside from the hot gases keeps it puffed up. Now, not all stars are created equal. The life a star leads depends almost entirely on its mass. Think of mass as a star's birthright, its destiny encoded in kilograms. Small stars, those with just a fraction of the mass of our Sun, are called red dwarfs. They're the quiet workhorses of the universe. These stars burn their hydrogen fuel very slowly, and as a result, they can live for trillions of years. In fact, because the universe is only about 13.8 billion years old, no red dwarf has ever died. They're like the ultra-marathoners of the cosmos, steady, quiet, and incredibly long-lived. Our Sun is a mid-sized star classified as a G-type main sequence star. It's been shining for about 4.5 billion years, and it has around 5 billion more to go. It converts about 600 million tons of hydrogen into helium every second. That's the equivalent of converting one Mount Everest's worth of hydrogen into helium every hour. And yet, it only uses a tiny fraction of its fuel each year. Stars are nothing if not efficient. As the Sun ages, the hydrogen in its core will eventually run out. When that happens, fusion will slow down and gravity will begin to take over again, compressing the core. This causes the outer layers of the star to expand dramatically. The Sun will swell into a red giant, growing so large that it may engulf Mercury and Venus, and possibly even Earth, depending on the exact details of its expansion. In this swollen state, the Sun will start fusing helium into carbon and oxygen, but it won't go much further than that. Mid-sized stars like the Sun don't get hot enough to fuse heavier elements. After a few million years of this new phase, the outer layers will be gently blown away into space, creating a beautiful glowing shell called a planetary nebula. What remains is the core, a small, dense, white-hot ember known as a white dwarf. A white dwarf is about the size of Earth but contains roughly half the mass of the Sun. It doesn't shine from fusion anymore, it glows with residual heat, slowly cooling over billions of years. Given enough time, it will become a cold, dark object called a black dwarf. But the universe isn't old enough for any black dwarfs to exist yet. Like red dwarfs, they're all waiting in the wings of cosmic history. Now for the big stars, the heavyweights of the stellar world. Stars with more than about 8 times the mass of the Sun lead dramatically different lives. These massive stars burn brighter, hotter, and much more quickly. Instead of living for billions of years, they might only last a few million. They're like cosmic rock stars, dazzling, intense, and gone too soon. As these stars burn through their hydrogen, they move on to fusing heavier and heavier elements. Helium to carbon, carbon to oxygen, oxygen to neon, and so on, all the way up to iron. But when iron forms in the core, the star faces a problem. Fusing iron doesn't release energy, it actually consumes it. So when a massive star builds up an iron core, fusion grinds to a halt. Without the outward pressure from fusion to counteract gravity, the core collapses in on itself in a matter of seconds. This sudden collapse triggers one of the most violent events in the universe, a supernova. The outer layers of the star rebound off the collapsing core and are blasted into space in a titanic explosion. For a brief time, a supernova can outshine an entire galaxy. It's a moment of destruction, but also of creation. The incredible heat and pressure of the explosion create elements heavier than iron, things like gold, platinum, and uranium. So yes, the gold in your jewellery and the iron in your blood were forged in the death throes of ancient stars. What's left behind after a supernova depends on the original star's mass. If the core was between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star, a city-sized object made almost entirely of neutrons. These stars are unimaginably dense. A single teaspoon of neutron star material would weigh about 1 billion tons. Some neutron stars spin rapidly and emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like a cosmic lighthouse. We call these objects pulsars, and they were among the most precise clocks in the universe. But if the original star was even more massive, the core collapses all the way into a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Black holes are not cosmic vacuum cleaners, as they're sometimes portrayed. If you replaced the Sun with a black hole of the same mass, Earth would continue orbiting it as usual. It would just be very dark and cold. Stars are not only vital to the universe, they are the universe. Their fusion furnaces create the elements, their light warms and nourishes planets, their death seed galaxies with the ingredients for new stars, planets, and possibly even life. The atoms in your body were once part of stars. You are, quite literally, made of stardust. Even more beautifully, stars are not static, they pulsate, rotate, and sometimes even have companions. Many stars live in binary or multiple star systems, orbiting each other in graceful cosmic dances. Some swap material, others orbit so closely they merge. Some create novas, temporary explosions that light up the sky before fading again. The lives of stars are full of variety and surprises. And let's not forget variable stars. Stars that change in brightness over time. Some do this regularly, others unpredictably. Studying these fluctuations has helped astronomers measure distances across the universe. Certain types of variable stars, like Cepheid variables, have a known relationship between their brightness and the time it takes them to dim and brighten. By comparing how bright they appear from Earth with how bright they should be, astronomers can calculate their distance. It's a bit like using a lighthouse beam to measure the width of the ocean. The night sky's filled with these glittering stories. When you look up at the stars, you're seeing light that's travelled for years, centuries, or even millennia to reach you. Every star you see is a message from the past. Some may have already ended their lives, their final light just now arriving at your eyes. Others are just beginning their luminous journey. In every direction, stars light the universe. They shape galaxies, ignite the cosmos, and provide the stage for everything else to unfold. And despite their unimaginable power, they do it all in silence. Just gentle points of light twinkling in the dark, keeping time with the heartbeat of the cosmos. Galaxies are the cities of the cosmos, grand sprawling metropolises made not of steel and concrete, but of stars, gas, dust, dark matter, and the occasional rogue black hole. They come in all shapes and sizes, some elegant and symmetrical, others chaotic and lumpy. If stars are the atoms of the universe's structure, then galaxies are the architecture, the vast gravitational neighbourhoods where the cosmic story unfolds. Take a moment to imagine what a galaxy actually is. A single galaxy can contain hundreds of billions of stars. Each of those stars may host planets, moons, comets, asteroid belts, and maybe even alien civilizations binge-watching interstellar soap operas. It's mind-boggling, and yet galaxies themselves are just tiny patches in the much larger tapestry of the universe. Our home galaxy, the Milky Way, is a barred spiral galaxy. It has a central bulge shaped like a bar, hence the name, with long curved arms that swirl outward like the whorls of a seashell. If you could see it from the outside, it would resemble a cosmic pinwheel stretching over 100,000 light-years across. But from our cosy spot inside one of its arms, we see it as a thick ribbon of stars stretching across the sky, the Milky Way, hazy and luminous on a clear night. The Milky Way contains somewhere around 200 billion stars, give or take a few billion. It's hard to count with that many zeros. But stars are just part of the story. The galaxy is also filled with gas and dust, interstellar material that forms nebulae, the birthplaces of new stars. Then there's dark matter, which we can't see or touch, but we know it's there because its gravity influences the motion of stars and galaxies. At the very heart of the Milky Way is something rather dramatic, a supermassive black hole called Sagittarius A star. It has a mass of about 4 million suns and sits quietly, or as quietly as a supermassive black hole can, at the galactic centre. Stars orbit it at breakneck speeds, whipped around by its immense gravity. We can't see it directly, but we've observed the effect it has on its surroundings, and even imaged its shadow. A remarkable achievement made possible by a global network of telescopes acting as one giant lens. The stars in a galaxy aren't just randomly scattered, they orbit the galactic centre in a kind of organised chaos. The spiral arms of galaxies are not fixed like the arms of a windmill, but rather areas of higher density that move through the galaxy like traffic jams on a highway. Stars move in and out of these arms, but the arms themselves persist, shaped by the complex interplay of gravity, rotation and density waves. Spiral galaxies like the Milky Way are among the most beautiful and well-studied, but they're not the only game in town. There are also elliptical galaxies, giant smooth blobs that range from nearly spherical to elongated football shapes. They don't have spiral arms and are generally filled with older stars. Elliptical galaxies can be small and unassuming or enormous, containing trillions of stars. They tend to be less active, with little new star formation, as most of their gas and dust has already been used up or blown away. Then there are irregular galaxies, the rebels of the cosmic community. They have no clear shape, just messy, chaotic blobs of stars and gas. Irregular galaxies often result from gravitational interactions or collisions with other galaxies, which can twist and warp them into all kinds of strange forms. Some are still rich in gas and forming stars at a frantic pace, while others are slowly fading into the cosmic background. Speaking of collisions, galaxies are not shy about running into each other. Unlike cars on a freeway, galaxies can and do collide, and fairly often, at least on cosmic timescales. These collisions happen over hundreds of millions of years, and because the space between stars is so vast, the stars themselves rarely hit each other. Instead, the gravitational forces involved pull and stretch the galaxies, triggering bursts of star formation and sometimes forming entirely new structures. Our own Milky Way is currently on a collision course with the neighbouring Andromeda Galaxy. They're about 2.5 million light-years apart, which sounds like a safe distance, but they're moving toward each other at about 400 kilometers per second. In roughly 4 billion years, they'll begin to merge. The night sky will be spectacular. Two galaxies slowly entwining, their stars intermingling in a cosmic ballet. Eventually they'll settle into a new, larger elliptical galaxy that some scientists are already calling Milkomeda. Galactic collisions don't always result in tidy outcomes. Some galaxies get torn apart. Others are consumed whole by larger neighbours. Dwarf galaxies, tiny galaxies with just a few billion stars, often orbit larger ones like the Milky Way and can be slowly absorbed, their stars scattered into the host galaxy's halo. It's a universe of mergers and acquisitions on the grandest scale imaginable. Galaxies don't live in isolation. They cluster together, bound by gravity into groups, clusters, and even superclusters. The Milky Way is part of the local group, a modest collection of more than 50 galaxies, including Andromeda, the Triangulum Galaxy, and several smaller dwarfs. This local group is itself part of the Virgo supercluster, which contains thousands of galaxies. And that supercluster is just one filament in the vast cosmic web, a structure that stretches across the observable universe. This cosmic web is one of the most astonishing discoveries of modern astronomy. When scientists map the positions of millions of galaxies, they find that galaxies are not distributed randomly. Instead, they form a giant network of filaments and nodes, like a 3D spiderweb made of light and gravity. In between these threads are enormous voids, vast regions of space with very few galaxies. It's as if the universe is organized on a grand architectural scale, with galaxies playing the role of glittering bricks in a dark and beautiful cathedral. Despite their vast sizes and distances, galaxies have distinct personalities. Some are active and turbulent, their centers blazing with energy. These are called active galactic nuclei, and they are powered by material falling into supermassive black holes. As gas and dust spiral inward, they heat up and release enormous amounts of radiation, sometimes outshining the rest of the galaxy combined. Quasars are among the most energetic of these, and they can be seen across billions of light years. They're like cosmic lighthouses shining through the darkness of the early universe. Other galaxies are more sedate, quietly glowing with the light of old stars. These galaxies may have used up their star-forming gas, or lost it through supernova winds and galactic collisions. But even these quiet galaxies hold secrets. Their stars, ages, and chemical compositions reveal histories stretching back to the dawn of time. Galaxies are also key to understanding the universe's expansion. In the early 20th century, astronomer Edwin Hubble discovered that galaxies are moving away from us, and the farther they are, the faster they're moving. This observation led to the realization that the universe itself is expanding, and it's been doing so since the Big Bang. The rate of this expansion is known as the Hubble constant, and measuring it accurately remains one of the major challenges in modern cosmology. Some measurements of the Hubble constant using the light from nearby supernovae and variable stars give one value. Other measurements, using the cosmic microwave background, the faint afterglow of the Big Bang, give another. This disagreement, known as the Hubble tension, may point to new physics waiting to be discovered. Perhaps dark energy, which is driving the universe's accelerating expansion, behaves in unexpected ways. Or maybe our understanding of the early universe needs refining. Whatever the answer, galaxies are the key. By observing them, mapping them, measuring their motion and makeup, we learn not just about their lives, but about the universe as a whole. They're our guides, our laboratories, our time machines. Looking up at the night sky, it's easy to forget that every tiny point of light might be part of a galaxy. And every galaxy is its own island universe, full of stories. Some are peaceful, some are wild, some are just beginning, others have long since gone quiet, but together they form the vast and beautiful ecosystem of the cosmos. So next time you see the Milky Way stretching across the night sky, know that you're looking at just one arm of one galaxy, a single glowing swirl in a universe filled with them. And though the scale is immense and the distance is unimaginable, each galaxy is a thread in the same cosmic fabric that weaves through you, me, and every atom in existence. Galaxies are not just places, they are the great luminous poems of space, written in starlight, dust, and time. Let's play a little game of cosmic hide-and-seek. Imagine peering through the most powerful telescope ever built. You scan the heavens and see a glorious spread of galaxies, stars, nebulae, and glittering dust clouds. But what if I told you that everything you can see, every twinkling star and radiant galaxy, accounts for only about 5% of the actual stuff in the universe? The other 95%, it's invisible, mysterious, and we only know it's there because of the odd ways it reveals itself through gravity and motion. Today, we're going to talk about one half of that hidden majority. Dark matter, the invisible web that holds the universe together. Despite the dramatic name, dark matter isn't ominous or spooky. It's just dark because it doesn't emit, absorb, or reflect light at all. You can't see it with a telescope. You can't touch it. It doesn't interact with normal matter in any way that we've been able to detect, except for one key thing: gravity. Dark matter has mass. It exerts gravitational influence. And that's how we know it's there. The idea of dark matter first crept into scientific consciousness in the early 20th century. Astronomers noticed something strange about galaxies. When they looked at the way stars orbit the centre of a galaxy, the math didn't add up. According to Newton's laws, stars farther from the centre should orbit more slowly, just like how the outer planets in our solar system move more sluggishly than the inner ones. But in galaxies, stars on the outer edges were orbiting just as fast as those near the centre. That meant one of two things. Either the laws of gravity were somehow broken on large scales, or there was more mass present than we could see. Mass that was exerting gravitational pull, keeping those fast-moving stars from flying off into space. This invisible mass was dubbed dark matter, and over the decades the evidence has piled up. Dark matter isn't just a quirk of one or two galaxies, it's everywhere. When we look at galactic clusters, huge conglomerates of galaxies held together by gravity, we see that there's way more mass than can be accounted for by visible matter. In fact, these clusters would fly apart without an extra source of gravity gluing them together. Another compelling clue comes from gravitational lensing. Remember how massive objects bend space-time and can bend the path of light. When astronomers observe distant galaxies through clusters of matter, the light from those background galaxies gets bent and distorted. By analysing the distortion, scientists can map the mass of the foreground cluster, and over again, the maps reveal more mass than we can see. Dark matter, warping space-time like an invisible hand. There's also the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in this ancient light contain clues about the early universe's contents, and when cosmologists crunch the numbers, they find that dark matter must have been present almost from the beginning, shaping the formation of galaxies and influencing the structure of the entire universe. So if dark matter is everywhere, what is it? That, dear listener, is still one of the biggest unsolved mysteries in modern physics. We know what it does, but we don't know what it is. There are several leading theories. The most popular candidates are WIMPs, weakly interacting massive particles. These hypothetical particles would have mass like regular matter, but would only interact via gravity and the weak nuclear force, making them nearly impossible to detect. Physicists have built elaborate underground detectors, shielded from cosmic rays and background noise, to try and catch the occasional rare interaction between a WIMP and ordinary matter. So far, results have been tantalizing but inconclusive. Another possibility is that dark matter is made of axions, extremely light, slow-moving particles that could exist in huge quantities throughout the cosmos. These particles are theoretical as well, but they might explain some of the peculiar quantum properties of the universe. Then there's sterile neutrinos, an even more elusive cousin of the neutrinos we already know. Neutrinos are ghostly particles that barely interact with matter and are produced in vast numbers in the sun, nuclear reactions, and exploding stars. If there's a type of neutrino that doesn't even interact via the weak force, it could be a strong dark matter candidate. Some scientists propose even more exotic explanations, like primordial black holes, tiny black holes formed in the early universe. These would be incredibly difficult to detect unless one happened to pass through a nearby region of space, which would probably make for an exciting but short-lived science news cycle. And of course, there are always the brave few who wonder if maybe we don't need dark matter at all. Maybe our understanding of gravity just isn't quite right on very large scales. Modified gravity theories attempt to adjust the equations to explain galactic motion without invoking unseen mass. While creative, these ideas haven't matched observational data as well as the dark matter hypothesis, at least not yet. Dark matter doesn't clump together to form stars or planets. It seems to be evenly spread throughout the halos of galaxies, forming a sort of invisible scaffold. Without it, the universe would look very different. Galaxies wouldn't have formed in the way they did. Stars wouldn't be arranged in the beautiful spirals and clusters we see today. Even the web-like structure of the cosmos, the filaments and voids that stretch across billions of light years, wouldn't exist. In many ways, dark matter is the quiet architect of the universe. It doesn't shine or explode or do anything flashy. It simply exerts gravity, shaping the evolution of cosmic structures over billions of years. And here's a fun twist. There's a lot more dark matter than ordinary matter. For every kilogram of regular matter, the stuff you and I are made of, there's about 5 kilograms of dark matter. That means you're vastly outnumbered by invisible cousins you'll never meet. But don't worry, they're not crowding your personal space. Dark matter doesn't interact with you, your chair, or your cat. It just passes through, like a polite ghost. To get a sense of scale, imagine a cube of space, 1 meter on each side. If you could somehow isolate and remove all the dark matter passing through that cube, you'd be left with only a tiny fraction of the total mass that was originally there. And yet, that ghostly mass is holding galaxies together and shaping the cosmos. The search for dark matter continues in labs around the world and far above it. Space-based telescopes and particle detectors buried deep underground are all part of the quest. Every year, scientists refine their models, build better detectors, and hope that the universe gives up just a little more of its secret. The irony, of course, is that the thing we call ordinary matter, the kind we see, touch, and build things out of, is actually the rare stuff. We named it ordinary because we live in it. But from a cosmic perspective, we're the odd ones out. Most of the universe is dark, silent, invisible, and still deeply mysterious. And yet, we've managed to infer its presence with nothing but mathematics, light, and curiosity. We've mapped its distribution by the way it bends starlight, calculated its influence by how it holds galaxies together, and modelled its impact on the earliest whispers of the cosmos. It's a powerful reminder that science isn't just about what we can see. It's also about what we can reason, deduce, and imagine. The universe doesn't owe us visibility, it only offers clues. And sometimes, the greatest mysteries are hidden in plain gravitational pull. So the next time you look up at the night sky, remember, most of what's out there you can't see. But that doesn't mean it isn't real. All around us, dark matter silently anchors the stars, weaves through the void and reminds us that even in darkness there's structure, and maybe, someday, understanding. The universe has always been on the move. Even when everything seems calm and still, stars twinkling gently, galaxies spinning with serene majesty, there's a secret momentum driving everything outward. Space itself is expanding, not like a balloon filling with air, but more like the fabric of space stretching, pulling everything with it. And what's behind this cosmic expansion? An invisible, elusive force called dark energy. It sounds like something straight out of a science fiction novel. Dark energy has that ominous ring to it, like a villain lurking in the background of the universe, twiddling its gravitational thumbs. But in reality, dark energy isn't malevolent or magical. It's simply mysterious. A kind of energy that fills all of space and seems to be responsible for pushing the universe apart faster and faster. To understand dark energy, we need to take a quick detour into cosmic history. Around 100 years ago, Albert Einstein was busy reshaping our understanding of gravity. His theory of general relativity described gravity not as a force, but as the warping of space-time by mass and energy. It was a bold idea, and it worked brilliantly. But when Einstein applied his equations to the universe as a whole, something strange happened. His math suggested that the universe should be either expanding or contracting. It couldn't just sit still. But back in Einstein's time, most scientists believed the universe was static and eternal, neither growing nor shrinking. To make his equations match this belief, Einstein added a fudge factor called the cosmological constant, a kind of built-in repulsive force to counteract gravity and keep the universe steady. Later, when Edwin Hubble discovered that the universe was actually expanding, Einstein called the cosmological constant his greatest blunder. The universe, as Hubble showed, wasn't just sitting there, it was stretching. Galaxies were rushing away from us in every direction, and the farther they were, the faster they moved. This expansion wasn't because galaxies were flying through space like fireworks, but because space itself was growing. Imagine raisins in a rising loaf of bread. The raisins stay in place, but the dough between them expands, increasing the distance between every pair of raisins. For a long time, scientists assumed this expansion was slowing down over time, gradually decelerating due to the gravitational pull of all the matter in the universe. That would make sense. After all, gravity pulls things together. But then, in the late 1990s, astronomers studying distant supernovae found something astonishing. They discovered that the expansion of the universe wasn't slowing down, it was speeding up. This was completely unexpected. If gravity were the only force at play, galaxies should be slowing their outward drift, like pebbles tossed into the air beginning to fall back down. But instead, they were accelerating. Something was pushing the universe apart and no one knew what it was. So scientists gave it a name: dark energy. Today, dark energy is believed to make up about 68% of the total energy content of the universe. That's more than 2/3 of everything. Ordinary matter, the stuff we're made of, makes up less than 5%. The rest is mostly dark matter. In other words, the cosmos is dominated by two invisible components: dark matter, which holds things together, and dark energy, which pushes them apart. The simplest explanation for dark energy is that it's Einstein's old cosmological constant come back to life. Not a blunder after all, but a real feature of the universe. In this view, empty space isn't really empty. Even the vacuum of space has an inherent energy. As space expands, more space appears, and with it, more vacuum energy. This causes the expansion to accelerate. But that explanation, while elegant, raises some tricky questions. If dark energy is just vacuum energy, why is its effect so small? Quantum field theory predicts a vacuum energy that is wildly larger than what we observe. Off by a factor of 1 followed by over 100 zeros. That's not a rounding error, that's a cosmic mismatch. Other theories suggest that dark energy might be a new kind of dynamic field, something that changes over time rather than staying constant. This hypothetical field has been nicknamed quintessence, borrowing a term from ancient philosophy where it meant the fifth element beyond earth, air, fire, and water. In this model, dark energy might have been stronger in the past or might change its behaviour in the future, altering the fate of the universe. Speaking of fate, the presence of dark energy has dramatic implications for how the universe will end. If dark energy remains constant, the universe will continue expanding forever, with galaxies drifting further and further apart until they vanish beyond the limits of observation. Stars will burn out, galaxies will dim, and the cosmos will cool into a cold, dark sea of silence. This chilling scenario is known as the heat death, or big freeze. But if dark energy grows stronger over time, we could be headed for an even more dramatic ending called the Big Rip. In this scenario, the accelerating expansion becomes so intense that it eventually tears apart galaxies, then solar systems, then planets, and finally even atoms themselves. Space would rip everything apart, starting slowly, then all at once. It's not likely based on current observations, but it's a mathematically possible outcome, which is enough to make cosmologists raise their eyebrows and maybe cancel long-term plans. On the other hand, if dark energy somehow reverses or turns off, gravity might regain the upper hand, halting the expansion and eventually causing the universe to contract in a big crunch. everything would collapse back into a dense, hot state, potentially followed by a bounce or a new beginning. While this idea was more popular before dark energy's discovery, it's still occasionally considered in alternative models. The trouble with dark energy is that we can't isolate it, poke it, or bottle it up in a lab. It's not something we can detect directly. We see its fingerprints on the universe, the way galaxies move, the way light bends, the way large-scale structures grow. But the energy itself, elusive. It's like trying to understand the wind by watching the trees sway. You know something's there, but it's invisible, untouchable, and maddeningly subtle. Scientists have designed massive surveys and observatories to try to unravel dark energy secrets. Projects like the Dark Energy Survey, the Euclid mission, and the upcoming Nancy Grace Roman Space Telescope are all aimed at mapping the universe with greater precision than ever before. By studying how galaxies cluster, how light stretches across space, and how structures evolve, they hope to reveal whether dark energy is constant or changing. There's also hope that advances in particle physics might offer clues. Maybe dark energy is connected to undiscovered particles or forces. Maybe it's tied to the geometry of extra dimensions. Or maybe it's a sign that our understanding of gravity itself needs an upgrade. Some theories propose modifications to general relativity on cosmological scales, bending the rules slightly to account for the accelerating universe without invoking an entirely new energy source. Wherever the answers lie, dark energy is a reminder that the universe still holds deep and profound mysteries. We've come so far in our understanding, from wondering what stars are to mapping galaxies, to uncovering the birth of the cosmos itself. But here, at the edge of everything we know, we encounter a force that defies explanation. It's both humbling and exhilarating. And in a way, it's fitting. The universe isn't a solved puzzle, it's a living, breathing enigma. Each discovery opens new questions. Each observation reveals new patterns. Dark energy might turn out to be a missing piece in a larger picture we haven't even imagined yet. Or it might be the key to a new kind of physics, one that reshapes everything we thought we understood. In the meantime, the universe continues its gentle, relentless expansion. Galaxies drift ever farther apart. Light from distant stars takes just a little longer to reach us. And all the while, dark energy works silently in the background, an invisible whisper, stretching the fabric of space itself, shaping the future of everything. The universe wasn't always the vast, star-speckled expanse we see today. In fact, if we could rewind cosmic history, not just a few centuries or even a few billion years, but all the way back, we'd find ourselves standing at the edge of something truly extraordinary. Not an explosion in space, but the explosive birth of space itself. The beginning of time, energy, matter, and every law that would ever govern the cosmos. This is the Big Bang. Not just a theory, but the best explanation we have for how everything began. The name Big Bang might give the impression of a loud, chaotic boom echoing through the void, but that's a bit misleading. There was no empty space for the universe to explode into, and certainly no sound. Sound needs air, and back then there wasn't any air to speak of. Instead, the Big Bang was the sudden rapid expansion of space itself from a state of incomprehensible density and heat. It wasn't something that happened in the universe. It was the universe, blooming from a tiny, hot, dense point into the cosmic arena we know today. So how do we know this happened? We can't exactly hop into a time machine and watch the universe form over breakfast. But the universe has left us some compelling clues, like a detective novel written in the language of light, motion and radiation. And perhaps the most eloquent clue of all is the cosmic microwave background. The cosmic microwave background, or CMB for short, is a faint glow that fills the entire sky. It's not visible to the naked eye, but it's there, all around you, passing through your body right now at a frequency too low for your senses to register. It was first discovered in the 1960s by two radio astronomers, Arno Penzias and Robert Wilson, who were trying to get rid of a persistent hiss in their radio antenna. They tried everything, even cleaning out pigeon droppings, but the hiss remained. What they had stumbled upon, quite by accident, was the oldest light in the universe. This light comes from a time about 380,000 years after the Big Bang. Back then, the universe was hot and dense, a glowing fog of particles and radiation. Photons, particles of light, were constantly bouncing off electrons and protons in an endless game of cosmic pinball. The universe was opaque, like the inside of a star, but as it expanded, it cooled. Eventually, it got cool enough for electrons and protons to combine into neutral atoms. This process, called recombination, allowed light to travel freely for the first time. That light is what we now observe as the CMB. It has been stretched and cooled over billions of years by the expansion of space, and today it's incredibly faint, with a temperature of just 2.73 Kelvin, barely above absolute zero. But it's still detectable, and it's full of subtle variations in temperature and density. These tiny fluctuations are like cosmic fingerprints, giving us clues about the structure of the early universe and the seeds of galaxies yet to form. The CMB is remarkably uniform but not perfectly so. It has minuscule ripples, differences in temperature on the order of 1 part in 100,000. These ripples are incredibly important. They represent regions where matter was slightly more or less dense, and over time, gravity amplified those tiny differences. The denser regions pulled in more matter, growing into galaxies, clusters, and vast filaments of cosmic structure. In a way, the CMB is the baby photo of the universe, showing the first faint hints of the cosmic architecture that would follow. But let's rewind even further. Before recombination, before stars, before atoms, what was the universe like in its very earliest moments? For the first tiny fraction of a second, far less than a blink, it was unimaginably hot and dense. Temperatures were so high that not even atoms or nuclei could exist. Energy was packed into a tiny space, and matter and antimatter were being created and annihilated constantly. Then something strange and dramatic happened. A period called cosmic inflation. Inflation was a brief but tremendous burst of expansion, occurring in less than a trillionth of a second after the Big Bang. During this period, the universe expanded faster than the speed of light, not because anything moved through space that quickly, but because space itself was ballooning at an incredible rate. Inflation smoothed out any wrinkles, stretched quantum fluctuations to macroscopic scales, and laid the groundwork for the structure of everything we see today. It might sound like science fiction, but inflation helps explain some puzzling features of the universe. For instance, why is the CMB so uniform in all directions, even though some regions of the sky could never have communicated with each other due to the limits of the speed of light? Inflation suggests they were once in contact, before being pushed far apart by the rapid expansion. After inflation ended, the universe continued expanding and cooling. Quarks and gluons settled into protons and neutrons. Within minutes, these particles began to fuse into the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium. This brief period, known as Big Bang nucleosynthesis, created the raw materials for everything that would come later. There were no heavier elements yet. Those would have to wait for stars to do their alchemical work. For the next several 100,000 years, the universe remained a hot, dense plasma. Photons continued to bounce around, unable to escape. But as we've already heard, once the universe cooled enough for electrons and protons to form atoms, light broke free and the CMB was born. After that, things went dark for a while. The universe entered what cosmologists call the cosmic dark ages. No stars, no galaxies, just hydrogen and helium atoms drifting through space. This lasted for hundreds of millions of years until gravity started pulling matter together, forming the first stars and galaxies in a process called reionization. When those first stars ignited, they re-illuminated the universe, lighting up the cosmic dawn. And from there, the universe blossomed. Galaxies formed, merged and evolved. Stars were born, lived and died, creating heavier elements in their fiery cores. Planets coalesced, and on at least one small rocky world orbiting a modest star, those atoms eventually formed oceans, trees, cities, and minds capable of looking back and asking, where did all this come from? It's a beautiful arc, from an almost featureless expanse of hot plasma to the rich, structured, star-filled cosmos we see today. And remarkably, we can trace much of that arc with confidence, using the evidence written into the light around us. The Big Bang Theory isn't just a guess. It's supported by multiple lines of evidence. The expansion of the universe, the CMB, the abundance of light elements, and the large-scale structure of galaxies. All of these point to a common origin, a beginning some 13.8 billion years ago when everything, space, time, energy, matter, began from an unimaginably dense and energetic state. And yet, the theory doesn't answer everything. What came before the Big Bang? That's a question that still stirs debate. Some physicists suggest that time itself began with the Big Bang, making before a meaningless concept. Others explore models of a bouncing universe where a previous cosmos collapsed and rebounded. Still others delve into multiverse theories, where our universe is just one of countless bubbles floating in a larger cosmic foam. These ideas are speculative and the evidence is still out, but that's part of the joy of science, knowing just enough to ask better questions. The Big Bang wasn't an explosion in space, it was the expansion of space. It wasn't loud because there was no sound. And it didn't happen at one particular spot in the universe, it happened everywhere, all at once, because space itself was coming into being. Every point in the universe today traces its origin back to that same moment. So when you gaze at the night sky, when you catch a glimpse of a distant galaxy, or feel the sun's warmth on your skin, you're touching ancient light. You're witnessing echoes of a beginning so profound that it continues to shape everything. 13.8 billion years later, here you are, on a tiny planet circling a middle-aged star, pondering the birth of all things. And in the faint glow of the cosmic microwave background, in the dance of galaxies, in the atoms that make up your breath and bones, you carry a piece of that beginning with you still. Black holes. The very phrase seems to pull at the imagination. They're the cosmic troublemakers, the mysterious voids, the bottomless pits of space that swallow everything and leave behind nothing. Or so the stories go. But as with most things in the universe, black holes are a little more complex and a lot more fascinating than their spooky reputation suggests. Let's start with what a black hole actually is. At its heart, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. It's the ultimate cosmic trapdoor. You can get in, but you can't get out. Or at least nothing can leave once it passes a certain boundary called the event horizon. This isn't a physical surface like the ground or a wall. It's more like a point of no return. Cross it, and escape is no longer an option. Now you might be thinking, wait, what's generating this gravity? Is there something inside the black hole, hiding behind the event horizon? That's the tricky part. Black holes form when a massive amount of matter gets squeezed into an incredibly tiny space. In most cases, they're born when a massive stars run out of fuel and collapse under their own gravity. The core compresses into a point of infinite density called a singularity, and space-time around it warps so drastically that it forms the black hole. Yes, you heard that right, a point of infinite density. That's what our current physics predicts, although most scientists agree that this infinity likely means we're missing something. A true theory of quantum gravity, one that unites Einstein's general relativity with quantum mechanics, would probably smooth out that singularity into something more manageable. But for now, in the equations, it's an infinite pit. Not all black holes are the same. They come in different sizes, with different personalities, if you will. The smallest type we know of are stellar mass black holes. These form when stars with at least around 8 times the mass of our Sun reach the end of their lives. The outer layers get blown off in a spectacular supernova explosion, while the core collapses into a black hole with a mass of perhaps 5 to 20 solar masses. Then there are intermediate mass black holes which are harder to find and understand. They weigh in somewhere between 100 and 100,000 solar masses. They might form from the mergers of smaller black holes, or from direct collapse of very large gas clouds in the early universe. We've found a few candidates for these mid-sized cosmic beasts, but they're still something of a mystery. And then we have the true giants, supermassive black holes. These titans sit at the centres of galaxies and can weigh millions or even billions of times more than our Sun. The one at the centre of the Milky Way, called Sagittarius A star, has about 4 million solar masses, and that's considered a relatively modest one. The largest black holes discovered so far are in the range of tens of billions of solar masses. That's like stuffing the mass of a small galaxy into a single point. How do supermassive black holes form? That's another ongoing puzzle. Some theories suggest they grew from smaller black holes that merged and fed over billions of years. Others propose that massive black holes formed very early in the universe, directly from the collapse of enormous clouds of gas before stars even existed. Whatever their origin, these giants are now found in the heart of nearly every large galaxy, including our own. So what happens near a black hole? As you approach the event horizon, things get strange. Gravity becomes extreme, and time starts to behave differently. Thanks to Einstein's theory of general relativity, we know that gravity warps time. The stronger the gravity, the slower time moves. This means that if you were to hover just outside the event horizon of a black hole, ignoring the engineering challenges involved, time for you would pass more slowly than for someone far away. To an outside observer, it would look like you're moving in slow motion. In fact, as you get closer and closer to the event horizon, you would appear to freeze in place, never quite crossing the threshold. But from your own perspective, you'd cross it just fine, assuming you weren't torn apart first. And that brings us to another delightfully named concept, spaghettification. Yes, that's a real scientific term. It refers to what happens when you fall into a black hole feet first. The gravitational pull on your feet would be significantly stronger than on your head, stretching you into a long, thin shape like a piece of spaghetti. This extreme stretching is caused by what's called tidal forces, the same basic mechanism that causes ocean tides on Earth, but dialed up to cosmic levels. The more massive the black hole, though, the gentler the tidal forces at the event horizon. So in theory, if you fell into a supermassive black hole, you might cross the event horizon without feeling anything at all, for a moment. Inside the event horizon, physics as we know it breaks down. Space and time swap roles. You can't avoid the singularity at the centre, just as you can't avoid tomorrow in the ordinary flow of time. It's your future, and all paths inside the event horizon lead to it. What happens at the singularity? No one knows. Our equations stop making sense. It's the place where the known laws of physics throw up their hands and say, "I give up." But black holes aren't just cosmic vacuums sucking in everything around them. That's a common myth. You can orbit a black hole just like you can orbit a planet or a star, as long as you keep a safe distance. If the Sun were magically replaced by a black hole of the same mass, Earth's orbit wouldn't change. We'd just be a bit colder and a lot darker. In fact, black holes can be surprisingly bright. Not the holes themselves, of course, but the material falling into them. As gas and dust spiral toward a black hole, they form an accretion disk, a swirling, flattened disk of material that heats up due to friction and gravitational forces. This disk can shine incredibly brightly, often outshining the rest of the galaxy. Some of the most luminous objects in the universe, called quasars, are powered by supermassive black holes devouring matter at a ferocious rate. As matter falls into a black hole, it doesn't always go quietly. magnetic fields and high-speed jets can channel some of the energy back into space, shooting out beams of particles that can stretch across thousands of light years. These jets are so powerful they can shape entire galaxies, regulating star formation and redistributing gas. So, in a strange twist, black holes, these symbols of destruction, also play a vital role in the creation and evolution of cosmic structures. For a long time, black holes were purely theoretical. Einstein himself wasn't a fan of the idea, thinking they were a weird quirk of his equations. But in recent decades, observations have confirmed their existence beyond reasonable doubt. We've watched stars orbit invisible points, observed gravitational waves from colliding black holes, and in 2019, we even saw the unseeable. The Event Horizon Telescope team released the first direct image of a black hole's shadow in the galaxy M87. That glowing ring of light, bending around a dark centre, was a breathtaking confirmation of general relativity and the reality of black holes. And speaking of gravitational waves, those ripples in space-time predicted by Einstein, they're now one of our main tools for studying black holes. When two black holes spiral into each other and merge, they release a huge burst of gravitational energy that travels across the universe. These waves were first detected in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory, marking the beginning of a new era in astronomy. We are now not just seeing the universe but feeling it too. Of course, black holes still hold secrets. There's the infamous information paradox, a puzzle that pits quantum mechanics against general relativity. According to quantum theory, information can't be destroyed, but if something falls into a black hole, it seems to vanish forever. What happens to that information? Is it lost in the singularity, stored in the event horizon, emitted back as radiation? This puzzle has led to ideas like holographic principles and black hole firewalls, wild but serious attempts to reconcile the laws of physics. One promising development came from Stephen Hawking, who showed that black holes aren't entirely black after all. Thanks to quantum effects near the event horizon, they can emit tiny amounts of radiation, what we now call Hawking radiation. This process allows black holes to slowly lose mass and, over unimaginable timescales, eventually evaporate completely. It's an extraordinary idea that even the most extreme objects in the universe aren't permanent. They live, they grow, and eventually they fade. Black holes challenge our understanding of space, time, energy, and information. They test the limits of our theories and force us to think beyond the familiar. Yet for all their strangeness, they're a natural part of the universe, a consequence of the same physics that governs falling apples and orbiting moons. So the next time you gaze up at the stars, remember, out there, somewhere, are cosmic shadows, silently shaping galaxies, bending light, and perhaps even holding clues to the deepest truths of reality. Mysterious, powerful, and endlessly fascinating, black holes remind us that the universe is not only stranger than we imagine, it's stranger than we can imagine. And that's exactly what makes it worth exploring. What if this universe isn't the only one? What if ours, with its stars and galaxies and oddly specific laws of physics, is just one bubble in a far larger, foamy sea of possibilities? It's a question that tickles the edge of science fiction and slowly, cautiously, makes its way into real scientific conversation. This is the idea of the multiverse, a term that suggests not just one universe, but many, perhaps infinitely many. It's a bold concept, and understandably it raises more eyebrows than it answers questions. But let's take a gentle stroll through the idea, because at its heart, the multiverse isn't just a wild theory someone cooked up after too much caffeine and not enough sleep. It's a natural outgrowth of some of our most successful scientific models. The more we understand about how this universe works, the more the possibility arises that it might not be alone. There are several versions of the multiverse idea, and each one comes from a different corner of physics and cosmology. Some are grounded in the math of inflation theory. Some pop out of quantum mechanics, Others arise from string theory. None of them have been confirmed, but they all offer tantalizing hints that our reality might not be the only show in town. Let's begin with inflationary cosmology, which we've already touched on. Right after the Big Bang, the universe underwent a period of rapid expansion called inflation, so fast that space itself ballooned outward faster than the speed of light. This helped explain why the universe looks so smooth and uniform across vast distances. But inflation theory, as it's currently formulated, doesn't necessarily stop with just our universe. In many versions of inflation, the expansion doesn't end everywhere at once. Instead, it stops in pockets, little patches of space that freeze out and become their own self-contained universes. The rest of space keeps inflating, and within that inflating space, new pockets continue to form. Each pocket becomes a universe, potentially with its own physical laws, constants, and conditions. This process is called eternal inflation, and it leads to a scenario where universes are constantly bubbling into existence like popcorn in a cosmic microwave. Our universe would just be one bubble in a vast, inflating foam of countless others. Now, if you think that sounds a bit wild, you're not alone. But the math checks out in many models, and eternal inflation is a well-explored idea in theoretical physics. We can't see these other bubbles. Space between them may be stretching too fast for any signal to cross, but their existence is not ruled out by the laws of nature. Next, let's hop into the strange and wonderful world of quantum mechanics, where reality itself seems to be written in a language of probabilities and possibilities. In the quantum realm, particles don't have definite states until they're observed. They exist in superpositions, being here and there doing this and that, all at once, like a cosmic game of Schrödinger's cat. One interpretation of this behaviour is the many worlds interpretation, proposed in the 1950s by physicist Hugh Everett. According to this view, every time a quantum event occurs with multiple possible outcomes, the universe splits into branches, one for each possibility. In one branch, the cat lives. In another, it does not. In one, you had toast for breakfast. In another, pancakes. In another, you slept in and missed breakfast entirely. Every choice, every interaction spins off a new branch, creating a vast branching tree of realities. In this scenario, there are countless versions of you, some very similar, others drastically different, living out different timelines in parallel universes. You'll never interact with them, but they exist, each one as real as the one you're in now. The many worlds interpretation has its critics, and it raises as many questions as it answers. But it's a legitimate interpretation of quantum mechanics, and it eliminates the need for wave function collapse. That strange snap where a quantum system picks one outcome over others when observed. Then there's the string theory multiverse. String theory is an ambitious framework that attempts to unify all the fundamental forces of nature by imagining that particles are not point-like dots, but tiny vibrating strings. The way these strings vibrate determines what kind of particle they are: electron, photon, quark, and so on. But for the theory to work, it requires extra dimensions, more than the familiar 3 of space and 1 of time. In some versions, string theory predicts a vast landscape of possible solutions, each corresponding to a different way the extra dimensions could be curled up or shaped. And each configuration leads to a different set of physical laws. So according to this view, there could be a staggeringly large number of possible universes, each with its own unique properties. Some would have stars and planets, others might be lifeless voids, or chaotic realms where atoms can't even form. Ours just happens to be one of the rare universes where the conditions are just right for life to emerge and wonder about such things. This leads to an interesting idea called the anthropic principle. If there are many universes with different properties, it's not surprising that we find ourselves in one that supports life, because we couldn't exist in any of the others. It's a bit circular, but it offers one way to explain the finely tuned nature of our universe's constants, like the strength of gravity or the mass of the electron. Maybe they're not finely tuned at all. Maybe we just happen to live in a universe where they happen to work for us. Of course, there are also more speculative versions of the multiverse idea. Some suggest that universes might branch off from black holes, with every collapsing star giving birth to a new cosmos on the other side of the singularity. Others imagine that our universe could be a hologram, a projection from a more fundamental reality. Still others propose that what we call the universe is just one region of a much larger megastructure, like a cosmic city with infinite districts, each separated by vast walls of space and energy. Do we have evidence for any of this? Not directly. That's the catch. The multiverse, in all its forms, is notoriously hard to test. If other universes are truly separate from ours, beyond our cosmic horizon, then we may never be able to observe them. But scientists are clever, and they're always looking for indirect hints. Some have searched for imprints in the cosmic microwave background, patterns that might suggest a collision with another universe in the early moments of the Big Bang. So far, nothing conclusive has been found, but the search continues. The multiverse raises deep philosophical questions as well. If there are infinite versions of you, what does that mean for choice, for identity? Are you still you if a billion other yous are making different choices somewhere else? These are questions without clear answers, but they're fascinating to ponder. And yet, despite all the mystery and speculation, the multiverse idea has a certain poetic symmetry. Nature often repeats itself. Galaxies form in clusters, trees grow in branching patterns, snowflakes form in familiar hexagonal geometries. Maybe, just maybe, the universe itself is not alone, but one of many. Maybe reality is bigger, stranger, and more layered than we ever dared to imagine. Even if the multiverse remains unproven, thinking about it stretches our minds. It invites us to imagine a cosmos that's not just vast in size, but vast in possibility. It reminds us that our little pocket of existence, our cozy corner with its carbon and starlight and morning coffee, is one chapter in a story that could have countless volumes. And that perhaps is the real gift of the multiverse. It doesn't diminish our universe, it expands it. It nudges open the door to a reality where curiosity, imagination and science all converge. A reality where anything that can happen does, in some distant fold of the cosmic tapestry. So the next time you find yourself staring at the stars, wondering about your place in the grand scheme of things, consider this. There might be countless versions of that moment, scattered like dandelion seeds across an infinite sky, each one a whisper of what could be. Each one part of the great cosmic chorus, singing softly just beyond the edge of what we can see. There's a gentle irony in the way we look at time. We wear it on our wrists, schedule it down to the minute, feel it rush when we're late and drag when we're bored. We treat it as a strict and steady ruler, ticking forward at 1 second per second. But in truth, time is a far slipperier thing than we like to admit. It bends, it stretches, it flows differently depending on where you are and how fast you're going. Time, it turns out, is one of the most peculiar elements in the cosmic equation. At a glance, time seems obvious. It's the thing that separates before from after, cause from effect. A dropped glass shatters but never unshatters. You remember the past but not the future, and every birthday candle you blow out is another lap on a track that only runs in one direction. But while time feels natural in daily life, the deeper we look into the universe, the stranger it becomes. Our modern understanding of time begins with the work of one particularly thoughtful patent clerk in the early 20th century, Albert Einstein. His theory of special relativity revolutionized the way we think about time by linking it inseparably to space. Before Einstein, time was thought to be absolute, universal, unchanging, and experienced the same way by everyone. But Einstein showed that time and space are part of the same fabric, space-time, and like fabric it can stretch, twist, and warp. According to special relativity, time isn't constant. It's relative to your speed. The faster you move, the slower time passes for you compared to someone at rest. This effect is known as time dilation. It's not just a theoretical curiosity, it's been measured. Astronauts on the International Space Station, moving at about 17,000 miles per hour, actually age slightly more slowly than people on Earth. It's only a difference of milliseconds over the course of a mission, but it's real. In fact, GPS satellites have to account for time dilation in their onboard clocks, or their positioning would quickly become inaccurate. And speed isn't the only factor that affects time. Gravity does it too. This is where Einstein's general theory of relativity comes in. According to general relativity, massive objects like stars and planets warp the fabric of space-time. The more massive the object, the deeper the warp, and the deeper the warp, the slower time moves. This means that time ticks a tiny bit slower at sea level than it does on top of a mountain. Again, it's a minuscule difference, but it's measurable with precise atomic clocks. The effect becomes more dramatic in extreme environments. Near a black hole, for example, time slows down drastically. If you hover just outside the event horizon of a supermassive black hole, you could experience only a few hours while years passed for someone far away. The movie Interstellar famously illustrated this effect with a planet near a black hole, where every hour equaled 7 years back on Earth. And while the details were exaggerated for storytelling, the underlying physics is sound. This warping of time leads to some fascinating possibilities and puzzles. For instance, could we ever travel into the future? Technically, yes. If you travelled at near light speed or stayed near a strong gravitational field, your time would pass more slowly than for people elsewhere. When you returned, you'd find that more time had passed for them. In a sense, you'd have travelled into the future. But what about going backward? That's where things get trickier. While general relativity allows for solutions that resemble time loops, called closed time-like curves, they require exotic conditions, like rotating black holes or hypothetical materials with negative energy density. And even then, most physicists think these solutions are more mathematical oddities than physically realizable time machines. More importantly, backward time travel leads to paradoxes. The classic example is the grandfather paradox. What happens if you go back in time and prevent your grandparents from meeting? Would you cease to exist? And if so, who went back in time in the first place? These paradoxes are one reason many scientists are skeptical of backward time travel being possible, at least in any meaningful sense. Still, time travel remains a rich area for both scientific speculation and philosophical musing. And speaking of philosophy, time raises some deep questions about the nature of reality. Is time truly flowing? Or is that just how we experience it? Is the present moment special? Or is it just one frame in a timeless film? There are different ways to think about time. The most intuitive view is called presentism, the idea that only the present moment is real. The past is gone, and the future hasn't happened yet. But another view, called eternalism, suggests that all moments in time exist equally, like pages in a book. In this view, the passage of time is an illusion, a trick of consciousness, as we move from one page to the next. Interestingly, physics tends to support the eternalist view. Space-time is often described as a four-dimensional block, with time as the fourth dimension. Events are laid out within this block, and nothing in the equations of physics singles out the present moment as special. This perspective is sometimes called the block universe theory, and while it's unsettling, it's consistent with our best understanding of the laws of nature. But if the laws of physics are time-symmetric, meaning they work the same forwards and backwards, why do we experience such a strong arrow of time? Why do we remember the past but not the future? Why does entropy increase? Eggs break but don't unbreak, and cream swirl into coffee but never unswirl. The answer lies in thermodynamics, specifically the second law of thermodynamics, which states that in a closed system, entropy tends to increase. Entropy is a measure of disorder or the number of possible configurations a system can have, and as time moves forward, systems naturally evolve toward more probable, higher entropy states. That's why a tidy room tends to get messy rather than the other way around. This increase in entropy gives time its direction. It's why we see cause followed by effect, not the other way around. But it also raises a question. Why did the universe start in such a low entropy state? That's one of the great mysteries of cosmology. The early universe was incredibly smooth and uniform, a very low entropy condition. Over time, gravity caused clumps to form, stars to ignite, and structures to emerge, increasing entropy along the way. Some physicists speculate that if we understood the conditions of the Big Bang more fully, we might uncover why time has the direction it does. Others wonder if our universe is just one part of a larger multiverse, where different regions have different arrows of time. It's all very speculative, but the questions themselves point to how mysterious and fundamental time really is. There's also a more recent and radical idea known as emergent time. In this view, time isn't a fundamental property of the universe at all. It's something that emerges from deeper, more basic rules. Just as temperature emerges from the motion of atoms, time might emerge from patterns of entanglement in quantum systems, or from some hidden, pre-time structure of reality. Some theories in quantum gravity, like loop quantum gravity or certain approaches to string theory, hint at the possibility that time isn't built into the universe at its most fundamental level. Instead, it may arise as a useful concept when we look at the collective behavior of countless tiny components. If this is true, our everyday experience of time is like the surface of water, smooth and continuous. But under the surface, reality may be choppy and discrete. It's a dizzying thought that the ticking of clocks, the rising and setting of the sun, even the beat of your heart, all of it could be just the surface tension of something much deeper and more mysterious. But even if time is emergent, that doesn't make it any less real to us. It's still how we navigate the world, plan our days, and understand our lives. Time binds our stories together. It turns experiences into memories, gives music its rhythm, and seasons its flow. It defines the journey from stardust to sunrise to sleep. Whether it's a fundamental axis of the universe or a mirage woven by entropy and consciousness, time is the stage upon which everything we know plays out. So the next time you glance at the clock or feel the days slipping by, take a moment to appreciate the strangeness of it all. Time isn't just ticking along, it's warping and bending, stretching and shrinking, whispering secrets from the depths of gravity and quantum fields. It's both the most familiar part of our lives and the most mysterious element of the cosmos. And maybe, just maybe, that mystery is part of the reason we find it so beautiful. If the universe had a soundtrack, it would be made of light. Not just the light you see, but all the electromagnetic waves humming through space, the microwaves that tell us about the Big Bang, the infrared glow of dusty galaxies, the ultraviolet sparks of newborn stars, and even the X-rays flaring from black holes feasting on matter. Light, in all its many forms, is how we know what we know. It is our cosmic messenger, carrying the stories of distant corners of the universe across the vast silent ocean of space. Despite how familiar it feels, light is deeply weird. It behaves like a wave and a particle, depending on how you ask it. It travels at the fastest speed possible in the universe, about 186,000 miles per second. And yet, from light's own perspective, it experiences no time at all. A photon, born in the heart of a star and travelling across the galaxy, doesn't age. It is, in a sense, eternally present. So what exactly is light? At its most basic, light is a ripple in the electromagnetic field, a kind of field that permeates all of space. When an electric charge jiggles, it creates a disturbance in that field, and that disturbance propagates outward at the speed of light. This ripple has both electric and magnetic components, oscillating at right angles to each other, and it carries energy, momentum, and information. The electromagnetic spectrum is vast and mostly invisible to our eyes. What we call visible light is just a tiny slice of it, wavelengths from about 400 to 700 nanometers. That's less than 1 octave on a piano of possible light. Longer wavelengths become infrared, then microwaves, then radio waves. Shorter wavelengths pass through ultraviolet, X-rays, and eventually into gamma rays. Different wavelengths of light reveal different aspects of the universe. Radio waves can pass through dust clouds, revealing cold hydrogen gas and pulsars ticking away in the darkness. Infrared shows us the heat signatures of planets and the birthplaces of stars. Ultraviolet light highlights hot young stars. X-rays reveal violent energetic environments like supernova remnants and the accretion disks of black holes. And gamma rays show us the most extreme processes of all, like matter annihilations and cosmic ray interactions. Because light travels at a finite speed, when we look out into space, we're also looking back in time. The moon is about 1¼ light seconds away, so we see it as it was a moment ago. The sun is just over 8 light minutes away. The nearest star system, Alpha Centauri, is a little over 4 light years away. That means if someone waved at us from there using a giant flashlight, we wouldn't see it until 4 years later. And the farther we look, the older the light becomes. When we observe distant galaxies, we are seeing them as they were billions of years ago. This ability to look back in time is one of astronomy's greatest superpowers. Using powerful telescopes, we can trace the evolution of galaxies, witness the births of stars, and even observe the faint afterglow of the Big Bang itself, the cosmic microwave background. This ancient light has been travelling for nearly 14 billion years, carrying with it a snapshot of the universe when it was just a few 100,000 years old. But light isn't just a passive messenger. It also interacts with matter in intricate and revealing ways. When atoms absorb or emit light, they do so in very specific patterns, fingerprints of sorts, known as spectral lines. Each element has a unique set of lines based on the energy levels of its electrons. By studying these spectral signatures, scientists can determine the composition of stars, galaxies, and even atmospheres of distant planets. That's how we know, for instance, that the Sun is mostly hydrogen and helium, with traces of heavier elements like oxygen, carbon, and iron. It's how we can spot water vapour in the clouds of an exoplanet or measure the redshift of a galaxy hurtling away from us at 1,000 miles per second. Speaking of redshift, light is also affected by motion. Thanks to the Doppler effect, when a light source moves away from us, its wavelengths get stretched, shifted toward the red end of the spectrum. When it moves toward us, the wavelengths are compressed, shifted toward the blue. This phenomenon lets us measure the speed at which galaxies are receding due to the expansion of the universe. It was this very redshift that Edwin Hubble used to discover that the cosmos is growing. But light doesn't just travel in straight lines. It can also be bent by gravity. Einstein's general theory of relativity predicted that massive objects like stars or galaxies would curve space-time around them, and that light would follow these curves. This bending of light is called gravitational lensing. It can magnify and distort distant galaxies, creating rings, arcs, or even multiple images of the same object. It's like the universe has its own natural telescope, allowing us to peer even deeper into the cosmos. Sometimes, gravitational lensing reveals galaxies so far away that their light has taken more than 13 billion years to reach us. We're not just seeing these galaxies as they were in the distant past. We're seeing them through cosmic funhouse mirrors shaped by dark matter and massive galaxy clusters. Light is also involved in one of the biggest unsolved mysteries of physics. Why is the speed of light the same for all observers, regardless of their motion? This constancy lies at the heart of special relativity. No matter how fast you're moving, if you shine a flashlight, that beam will still travel at the speed of light relative to you. This defies our everyday intuition. If you throw a ball from a moving car, it goes faster relative to someone on the sidewalk. But not light. Its speed is an absolute limit. a kind of cosmic speed cap. This limit has profound consequences. Nothing can accelerate to the speed of light if it has mass. The closer you get to light speed, the more energy it takes to keep accelerating. At the speed of light, your mass would become infinite and time would stop. So, as much as we'd love to zip across the galaxy at warp speed, nature has drawn a firm line in the sand. Yet photons, particles of light, can do what we cannot. Because they have no mass, they move effortlessly at the speed of light, and in doing so, they connect the universe. They link stars to planets, galaxies to telescopes, ideas to evidence. Light is how we know the universe exists beyond our own little patch of rock and sky. There's also a delightful twist to the story of light. It behaves both as a particle and a wave. This is known as wave-particle duality. In some experiments, light behaves like a wave, interfering and diffracting as it passes through slits or around edges. In others, it acts like a particle, arriving in discrete packets of energy called photons. This dual nature is at the heart of quantum mechanics, and it's one of those concepts that feels almost magical until you accept that the universe is under no obligation to behave the way we expect. In fact, the quantum behavior of light has opened up entirely new frontiers. Quantum optics, for example, explores how individual photons can be manipulated for technologies like quantum communication and quantum computing. Lasers, which depend on precise control of light at the quantum level, are now everywhere, from barcode scanners to eye surgery to cutting-edge physics experiments. Even more exotic is the idea of entangled photons, pairs of light particles linked in such a way that measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, defies classical intuition, but has been repeatedly confirmed in experiments. It hints at a deeper layer of reality, one where information and connection transcend space and time. Light has also been our guide in exploring the planets. From the first telescopic observations of Mars and Jupiter to modern missions analysing the reflected light from alien atmospheres, we've used it to study the weather on Saturn, the surface of Venus, and the frozen moons of Jupiter. We've watched comets flare, dust storms rise, and auroras dance, each one telling its story in wavelengths our eyes alone cannot see. And of course, light is essential not just for seeing the cosmos, but for life itself. Sunlight powers photosynthesis, drives the climate, and regulates our biological clocks. The rhythm of light and dark is stitched into our biology, guiding sleep, mood, and metabolism. On some distant worlds, perhaps light plays a similar role, nurturing strange alien ecologies bathed in red suns or blue-white stars. In the end, light is both a scientific tool and a poetic symbol. It reveals the hidden, guides the curious, and connects the vast to the intimate. Whether it's crossing the void from a distant galaxy, bouncing off the moon, or simply spilling through your window at dawn, every photon carries a story, one written in the language of the universe itself. So the next time you strike a match, flick on a lamp, or watch the stars twinkle in a quiet sky, take a moment to marvel at this strange, beautiful ripple of energy, because in every glimmer, every shimmer, every beam and glow, you're witnessing the same force that brought us the first look at the beginning of time, and may one day show us how far there is still to go. And so, our cosmic tour gently winds to a close. We've drifted through the tiniest quantum realms and soared across the grandest galactic tapestries. We've watched stars ignite and die, black holes twist time itself, and light carry messages across billions of years. We've pondered what came before the Big Bang, imagined other universes, and questioned the nature of time. It's a lot to take in, perhaps even too interesting for bedtime. If you're still awake, well, I hope you found it a peaceful kind of fascinating. And if you drifted off somewhere between quantum fields and stellar nurseries, that's perfectly fine too. Either way, you spent time with the universe tonight. Before you go, I'd love to hear, where in the world are you listening from? And what time is it right now? Midnight in Melbourne? sunset in Seattle? Let me know in the comments. It's always amazing to see how far this sleepy little spacecraft travels. And if you enjoyed the journey, whether it helped you unwind, learn something new, or simply brought a moment of calm, please consider leaving a like or subscribing. It truly helps support the channel and keeps these gentle explorations going. Thank you for joining me. Rest well, dream deeply, and remember, the universe is vast, beautiful, and always waiting to be wondered about.